Do you know half of their lives humans walk in a cognitive slumber? Well, a part of it owes when we don't have an idea to where we are headed. Well, antidote to clarity is having right mentors and the right guidance. Hello everyone. DSA Carnival 2.0 is back with amusing insights on the subject to make a programmer's work as flat as a pancake. Welcome to the session on recursion. Prior to beginning with the session, I might want to enlighten you regarding DSA Carnival 2.0. It will be a 10 days course and will be streamed on our YouTube channel. After the completion of the course, students will be provided with some quizzes to test their understanding. Well, that is not it. We have a lots of prizes in store for all the participants who participate in the quiz. So just gear up and watch out this 10 days exciting journey. I would first like to thank Geeks for Geeks and Coding Minutes to sponsor the event. Moving further, it's a great pleasure for me to introduce our speakers today. Get an expertise on your coding skills with our speakers for today, Mr. Rahul Lather, who is a six-star at Codechef and has an excellent expertise in problem solving and competitive programming. Being a member of technical staff at Coding Ninjas, he has been building a code studio to provide students with a great platform to wrestle their knowledge up for coding. Today, he will dive into the spooky topic of recursion, which makes our blood run cold. Thank you so much, sir, for joining us. We all are super excited to have you here. Excited about the amazing session we are gonna have today. Over to you, sir.
Hi Mansi, thanks for inviting me for the session and the whole team for organizing this event. Right. So, so I think directly we can start now, right? Just to confirm, before can anyone confirm whether my voice is audible and nothing is lagging? Can anyone comment if my voice is audible or not? Okay, okay, okay. So it seems everything is going fine. So okay, so today's, as all of you are aware, that our topic of discussion is recursion, and I think that is the most important topic going forward for DSA. Basically, it is like the mostly used in trees, graph concepts, right? And it also helps solving lot of problem by an easier method, right? A lot of time you are gonna compare that solving a problem using iterative methods, that is using for loops or while loops, is gonna tough, and with the recursion it makes really easy, right? So okay, so let's just start with our topic with a basic definition. So basically, recursion is nothing but just whenever a function call itself inside the function, so it will be called as recursion, right? So we will gonna be see exactly how what this definition means. So let me, so let's just directly jump into an example. Our first example, where we will be finding the factorial of n, right? All of you are must aware of factorials, right? What a factorial is, as we have read about it in basic mathematics. So basically, a factorial is nothing but the factorial of n is nothing but just a multiplication of first n natural numbers, right? So factorial of 1 is 1, and 2 factorial is 2. Similarly, 3 factorial is 6, because 1 into 2 into 3 is 6, right? And similarly, we can find that factorial of 5 is 120, right? So I hope all of you are aware that what a factorial is, right? Just confirm that the definition of factorial is clear to all of you. Okay, so let's just directly see how we will proceed solving this problem, and we will also be gonna see how this can be converted to a recursion and what actual recursion is, right? So let's just first try some formula and see how we are converting any problem to a recursion, right? So as you can see, n factorial can be written as, I can say, just a second, the sum of first n numbers, right? N into n minus 1, then going through 3 to n 1. So we can also represent this n factorial as n into n minus 1 factorial. Okay. So, like, can you confirm that if we know the factorial of n minus 1, we can easily calculate n factorial, if I am right? Does everyone got this point? Can anyone confirm? Okay. So it means like, if we know the n minus 1 factorial, we can easily find n factorial, right? So, and if you see n minus 1, calculating n minus 1 factorial is a smaller problem as compared to n factorial, right? So this is the funda where we can try thinking of recursion, because recursion is basically like calculating smaller problems first and then using those results to calculate the original problem. So here the smaller problem is n minus 1, right? And if we know the results of n minus 1, we can easily calculate n factorial, right? So let's just see how we will proceed, and what algorithm we can write to solve this problem. For simplicity, let's just write a simple method that is fact. Just a second. So here I have represented this fact method, which return type is integer. Sorry. So integer, basically it will return the factorial of n. N will be provided as an argument, and we will return the factorial of n, right? So by this method, fact 5 should return 120, as the factorial of 5 is 120, right? And the formula, you can say, factorial of n should be equals to n into factorial of n minus 1, right? So by using this formula, we will be writing some lines of code inside this method. Okay. So the very first line is basically, as we discussed, that we should first calculate the result of smaller problems. In this case, our smaller problem is n minus 1, and whatever it will return, we will call it as small answer, right? So for now, let's just assume that we know small answer, that is the factorial of n minus 1, right? And if we assume that this method will give us correct results, so we will simply multiply it by n and return our original answer, right? That will be the factorial of n, that is n into small answer. Okay. So just a second. So can anyone, if you understand functions, right, you must be aware of how to try run this code. And can anyone confirm the output of factorial of 3? What will this method give us output? Factorial of 3 for this method, if we pass n equals to 3 as an argument, so we can calculate that just in few minutes. Anyone who can confirm? Okay, Lakesh said it's 6. Anyone else? There might be some issues in the code. You can also check that. Okay, so let's try seeing how exactly this code will run. Okay. Anyone else wanting? Yeah. Okay, so let's see the steps of execution for this code. that I have mentioned on the right side. That okay, so when we call our method with fact 3, that is n equals to 3, so fact 3 will be called, that is our first function call to recursion, right? And then fact 3 will execute its first statement, that is small answer equals to fact 2. So basically it is asking the same method that first give me the result for 2, then I will be calculating further steps to calculate the factorial of 3, right? Before that I can't calculate the factorial of 3. That is the funda of recursion. So it is calling itself to know the answer for the smaller problem here, that is 2. And now 2 will 2 will call further the smaller problem, that is 1. Basically if it knows the answer for 1, then only we can calculate factorial of 2, right? So if we see, this will keep going on, and 1 will call 0, then 0 will call minus 1, and until minus infinity, right? Because we are only decreasing n by 1 each time and calling the function again and again, right? There is no condition specified where should we stop, right? So if we are not specifying any condition to stop, then it is not gonna stop or throw some error, runtime error. In some languages it basically throws stack overflow, because all the functions calls are stored in a stack. So as we have a very limited space for program execution in stack, so if we are going up to certain limit, then it will definitely gonna throw runtime error, right? So yeah. So now can you, anyone confirm what could be the condition we can specify to stop our program? Any condition? Okay, Lakesh has suggested us one condition. If n equals to 1, then return 1. Right. And what if we are given n equals to 0? Right. If we specify that condition, then we might be uh, for the answer for n equals to 0, right? So let's just see some definitions here. So first of all, as we have discussed, there should be some condition to stop our execution, right? So for that we use base case in recursions. So base case is nothing but just a way to stop our recursion executing till infinite number of times, right? Infinite number of times. So now our aim is to keep dividing the problem. So while using recursion, our aim is to keep dividing the problem into sub problems until we reach a specific point where we can definitely know the answer for that problem, right? So if we have reached to a very small problem, that is the base case of our problem, and we can say that okay, the answer to this is well defined. We don't need to call other sub problems or going further. We can directly return our result from there. So that is a base case, and that is our aim to like solve problem recursively. First of all, every time we will identify base cases of each problem and what sub problems we can use to divide any large problem, right? So for our example, what should be the base case, as we have already discussed, and some of you have also mentioned that we can use 1 or 0 based on our constants. That if we are calculating the factorial of all numbers that are greater than 1 or further, so we can use base case as 1. And if someone has mentioned that n can also be 0, then we can use 0 as well for the factorial, right? So now if you see the code on the right side, we have mentioned the base case as if n is 0, then we are gonna return 1, because factorial of 0 is well defined that it's 1, right? So now if we see that when we execute the factorial 3 of using this code, right? And then 3 will, as we have discussed, 3 is gonna call 2, then 1. Now after 1, so after 1, when it the call goes to 0. When factorial of 1 calls 0 to give its result, right? So now the call is in factorial of 0, n is 0. When we enters the first line of our method, we met that condition that n is 0. Okay, so we will return 1, right? Factorial of 0 will be returning 1, and there will be no further execution of statements and no calls will proceed further in the recursion, right? Anyone having any doubts till yet? Okay, so let's jump directly to the next part. Okay, so as factorial of 1 has already calculated the small answer for factorial of 0, that is 1, right? Now, when it executes the return statement, it will simply multiply itself and the small answer, that is 1 and 1. So it will return 1. Okay. So for factorial of 2, the factorial of 1, that is small answer, is 1. Then simply it will multiply itself with 1 and then return 2 into 1, that is 2. So here the factorial of 2 has already calculated its answer, that is 2, and will return its answer to 3, the call of 3, right? So this way the factorial of 3 has received the result for its smaller problem, that is 2, and it will multiply itself by 2 to calculate its factorial, right? So the result will be 6, and the factorial of 3 you can also verify it will always be 6, right? Just a point to mention here that every function call, if you see, we are calling the same method by same name each time, just different parameters. But each time, whenever a function is called, either it is calling itself or any other function, it is it is stored in a separate memory location, right? That is known as stack in case of recursions, right? So each function call will be stored in a storage separate space. It is not the same as before, and all the variables or primitives that we have initialized in each call will be different. If you see that, let's just see, we have you can say n is passed as an argument to each call, that is 3, 2, and 1. Each time n is different and is changing. This is not the same method that is executing, right? So each time the function will be initialized separately and will called and will be executed separately in the memory. Just want to clarify that. Okay. So does anyone have any doubt before we are jumping to our next problem? We will be seeing basics of recursion today, right? Okay. Just as question, as you guys have already read about or studied about integers or data types in these lectures. So can anyone confirm whether this code will run for large numbers, or like till what values of integer this code can work? Or did anyone got the question? Hitan said yes, it should. Okay. Aman has said still it's not exit 10 raised to power 9. Yeah, Ar- Arman is correct that it will only will calculating its result correctly till the answer has not reached 10 raised to power 9, as integer has certain limit to store the results, right? So you can try running a factorial value for 30 or 50, some large numbers, that this program will give you very uncertain results, sometime negative, so sometime positive, even a very less value for 50 in a positive number. So that is because of memory, or you can say data type overflow, that if you are storing result that are that cannot be stored in an integer that exceeds the range of 10 raised to power 9, then it will be going to going to give uncertain results, right? So yeah, there is a certain limit to this method, and we can also extend this to using long data types here if we are trying to execute exceeds our range, right? Okay, so I think this problem is clear to each one of you. Let's see another basic problem. Basically, it's a version of multiple recursion, you can say. In previous problem, we have seen that we are only calling one problem, or you can say one call inside our method. So each function call is calling only one recursive call, right? Now we are seeing a very basic example of multiple recursive calls, and how base cases may vary depending on whether we are calling only one call or whether we are calling multiple calls, right? So did every one of you have heard about nth Fibonacci number or Fibonacci series? Okay, I think you guys are aware of that, and I think you guys have also tried printing Fibonacci series iteratively, right? So now, when if we are trying the Fibonacci series printing, or you can say finding nth Fibonacci number using recursion, that will be a different concept than iteration, right? So yeah, let me first explain what a Fibonacci series is. So here I've written a series 0, 1, 1, 2, 3, 5, 8, and going on. So if you see, each number is a sum of previous two numbers, right? So you can see first two numbers are fixed in the series, that is 0 and 1. Then the sum of 0 and 1 will be the third number, the third integer, or you can say the third term of the Fibonacci series, that is 1. The fourth Fibonacci number will be sum of the first and the second, that is 1 and 1. So fourth Fibonacci number will be 2, and similarly 1 plus 2 will be 3, and then you can say 2 plus 3 is 5, and 5 plus 8 is 13, going on. The last number I mentioned is 34, which is sum of its previous two numbers, that is 13 and 21, right? So Fibonacci of 0 is 0, right? Fibonacci of 1 is 1, Fibonacci of 9 is 21. So in this way we have to calculate the nth Fibonacci number, right? So as we have discussed, while solving problem recursively, we should first think of a base case, and our second condition is we should try dividing the problem into smaller problems, and write some recurrence relations, right? Basically recurrence relation is nothing but the, you can say, a formula that will help us calculating the original problem. So here, as I've written, Fibonacci of n equals to Fibonacci of n minus 1, that is its previous term, plus Fibonacci of n minus 2, that's the last second term. Okay, so this is a recurrence relation for this problem, right? Why this recurrence relation? Because if we know for sure the value of n minus 1 and n minus 2, they are Fibonacci numbers, then we can definitely calculate Fibonacci of n. Okay, so, and before writing the basic method, what should be the base case, right? We should also have considered that. Let's just think, as we have seen previously, that 0 is the lowest term, that is the lowest sub problem, that whose answer we are aware of, right? So if we write or decide considering the base case as 0, that if n is 0, then we are gonna return 0, right? So that is our base case. And now we are calculating two small answers, that is Fibonacci of n minus 1 and Fibonacci of n minus 2, right? If we know these two answers and we return their sum, then we can calculate the Fibonacci of nth number, right? So can anyone calculate the result using this method for Fibonacci of 2? If we have followed through, we can easily calculate the Fibonacci of 2 using recursion with this method, right? So does anyone got the answer for Fibonacci of 2 using this method? Okay, so let's just try dry running our code and see what results we can get. Okay, we have mentioned the base case. We are using the small answers to calculate our original answer, right? Let's just see. Okay, so let me note that. Okay, so when we are calling the Fibonacci 2, right? And one thing I want to mention here that whenever you are solving the problems recursively, always try a tree representation or something using your copy, or you can write anywhere. Always try to visualize the function calls, right? Only then you can solve complex recursion problems, right? And with practice, when you have enough practice, you can easily visualize those things inside your mind as well. So first, if you make a strong practice and try visualizing the recursion functions, then you can easily do that without using a copy pen or anything. Okay, so let's just see how Fibonacci 2 can be calculated using that method. If you see this method, you can check. We have mentioned the base condition as n equals to 0, right? And we are calling two calls, that is first n minus 1 and then n minus 2. Okay, so first of all, let's just call Fibonacci of 2, and our as base condition will not met because n is not 0, we will call our first recursive call, that is Fibonacci of 1, right? And after that, can anyone say which call will gonna happen? Like whether we are calling Fibonacci of 0, that is the second subproblem of 2, or we will call the first subproblem of Fibonacci of 1. Which call will gonna make? Let me repeat the question again. So should we call the second subproblem of Fibonacci of 2, that is Fibonacci of 0, or now we will call Fibonacci of 0, that is the first problem of Fibonacci 1. So which statement will be executed first? Fibonacci of 0, but Fibonacci of 0 for what? As a second subproblem of Fibonacci of 2 or first subproblem of Fibonacci of 1? Okay, few guys have mentioned Fibonacci of 0 as first subproblem, and one guy has mentioned Fibonacci of 1. Hitans just said Fibonacci of 1. Okay, so let me confirm the. We are gonna call the first problem of Fibonacci of 1, right? And let's just see how we can prove that. Before that, I would recommend just try some more time using copy and pen and draw the recursive calls. Okay, so let's just jump back to the code, right? When we started with our first code, that is Fibonacci of 2, I think we can use a sample. Okay, so let me just stick to that. Okay, so when we have called our first call, that is Fibonacci of 2, we first met this base condition that if n is 0, which is not the case, so we have skipped this base case. Now we executed our first statement, that is Fibonacci of n minus 1 for n equals to 2. So n minus 1 will be 1. We have called Fibonacci of 1, that is the first subproblem of 2, Fibonacci of 2, right? Now when Fibonacci of 1 is called, so we have entered into a completely new method, and we can't go back to Fibonacci of 2 before completing this method, right? So now if we have entered Fibonacci of 1, we can't go back until we have executed this method. So we should complete this method first. And when we have called Fibonacci of 1, sorry. So if we have called Fibonacci of 1, if you try executing this completely new method, the base condition is again skipped and the first subproblem should be called, right? That is Fibonacci of 0. Okay, so Fibonacci of 0 will be called, but it will be called as a first subproblem of Fibonacci of 1, not for Fibonacci of 2, right? Okay, so and now we have mentioned the base case that if n is 0, we will return. So no further calls will be made and we will return our result from here. So as we have returned our result, now we can move back to its parent. You can see it's, if you see it's as a hierarchy, Fibonacci of 1 is parent of Fibonacci of 0, right? So now we have jumped back to Fibonacci of 1, and Fibonacci of 0 has said that okay, I have calculated my result. Now you can call your second sub problem, that is n minus 2, right? So Fibonacci of 1 will call n minus 2, that is Fibonacci of minus 1, right? So this way the second sub problem will be called only if the first sub problem has completed all of its executions that are under that, right? And now if you see the interesting part, we have entered again the negative numbers, and if you see, we keep going on, we will keep going on, right? This will call its up first sub problem as minus 2, then it will call as minus 3. This will not gonna stop because our base condition was 0, and once we entered negative numbers, n minus 1 and n minus 2 all calls will keep executing further, and once again we met with a runtime error or stack overflow, right? As the program will keep executing. So now if you see, if you analyze, there should something, some, or you can say some more condition or base condition that we should add to stop our calls, right? To stop our program to execute infinite number of times. Can any one of you suggest what base condition we have missed, or what other base condition we can mention to stop calls before executing further? Anyone? And remember, the condition, whichever condition we are mentioning, the answer for that condition should always exist and is well defined, right? So what should be another base condition that? we can use here. Okay, Jatin just said if n is less than 2, return n. Okay, anyone else? Any other answers? Yeah, I think his answer also gets the right answer. That if n is less than 2, that is if n is either 0 or either 1, we can simply return n, right? As Fibonacci of 0 is 0, Fibonacci of 1 is 1. So we can choose those two as our base cases, and we will see that how many base cases we can choose and why we have only choose two base cases here, right? So let's just use another base case, that is if n is 1 then return 1. You can also combine both cases here, that if n is less than 2 we can return n, because if n is 0 we are returning 0, if n is 1 we are returning 1. So we can also write that if n is less than 2, return n, right? Everything else will remain same. It was just a miss of for a base case, right? Now if we see, let's just see what will be the output for Fibonacci of 4, right? And we will also verify why there are only two conditions, why not more, not less, right? And let's just see the tree representation of this method, that if we call Fibonacci of 4, right? Okay, so here I have represented the function calls in a tree shape, that we have started with Fibonacci of 4, that is the root of the tree, right? And as we have discussed, we will always execute our first subproblems before going to the second subproblem, right? So Fibonacci of 4 will call Fibonacci of 3 to give or calculate its results. Then simply 3 will call 2 and 2 will call 1. And we have mentioned 1 as our base condition. So 1 will simply return 1. Okay, now 2 can call its second subproblem, that is Fibonacci of 0. And we have also mentioned 0 as our base case, so 0 will return 0. And Fibonacci of 2 will simply do sum of these 1 and 0 and return 1, right? Now for Fibonacci of 3, we have already calculated result of its subproblem, that is Fibonacci of 2. Now it will go to its second call, Fibonacci of 1, and it will return 1 because the base condition will met. And similarly, you can see on the right side of Fibonacci of 4 that 2 will be its second subproblem because n minus 2 is 2, and 2 will call 1 and 0 at its two subproblems, right? Okay, so if we see that we have only mentioned two subproblems, right? Why two problems? We have seen that we are not completing our executions with only one base condition, and we can see that we have successfully calculated our result for two conditions, right? So there, as there were two calls, and the formula generated, that is n minus 1 and n minus 2, is giving two new subproblems. So that's why we should always first verify those two subproblems with base cases, that what should be the least value that can go through each subproblem, right? As we have mentioned, only the base case is 0, but when we come to Fibonacci of 1, then second problem can go to n minus 1 as well, right? So that's why we should stop at 1 also, right, before calling it second subproblem. Okay, so in this way we have calculated our results. So there were only three parts to our recursion function. If you see, one is a base condition, that always try to come up with a base condition. Just a second. Okay, so whenever you have got a problem and you can divide that problem into sub problem, first you should find out a recursive relation for that problem, whether you can solve that problem using smaller problems, right? Let's say if you need to calculate the sum of n natural, or you can say the sum of an array, all the elements of an array, right? If you try thinking that, or try dividing it as a sub problem, so you will see that if I know the sum of the n minus 1 element, right? If I assume that I have the sum of n minus 1 elements, I can easily calculate the sum by adding that sum to my first element, right? So that is an example of sub problem. If you can divide any problem to a sub problem and just leave that to recursion, okay, recursion will definitely give me the result for this sub problem. I only need to think, if I have the result of that sub problem, how can I use that, how can I use the result of that sub problem to calculate the original answer. As in these cases, we have just assumed recursion to give the result for Fibonacci of n minus 1 or n minus 2, right? And we just left our recursion to calculate those results, and we just use them and did some calculations to calculate the original results, right? So only three conditions: one is base case, one is the recurrence relation, and third one is calculations. What calculations you can do based on those recursive problems or recursive results to calculate the original result. If you can think these three things, then you can solve any recursive problems very easily, right? Did anyone have any other questions before we wrap up our this session? I think we have some time left, then we can discuss any of your doubts. Okay, I mentioned here as well that only there are three things: base case, recursive calls, and a small calculation. Okay, Arman has said what is the maximum recursion calls possible in CPP. It is a language dependent. For Java, you can call around 3,000 or 4,000 recursive calls in at one time, right? So if you see that representation of tree, that at maximum time we have used here four calls, that is Fibonacci 4. When the Fibonacci 4 will be called, it will go to stack, right? Then 3 will added on the top of stack, then 2, then 1. On 1 we will stop, and at this point there are maximum 4 calls, so it means we have used 4 memory spaces. So in this way we can only go to 3,000 or 4,000 number in Java. In CPP I think it's around 10 raised to power 5, and in Python it's around 500 or 1,000, but you can extend those limits using some libraries in Python. For Java it will be around 3,000, and neither you can't accept. That's why even you will see, if you write codes in Java using recursion, then you will get memory overflow or stack overflow after, for let's just take it as an exercise. And if you try calculating Fibonacci, or you can say factorial of n for 5,000, it will throw you stack overflow, but in C++ it will not throw. Okay, Hitan said it is difficult to figure out how to apply recursion in big questions. Uh, okay, first of all, like, you should not directly jump to, like, really tough questions of recursion. And if you have practiced very basic questions, and if you are trying to solve big questions, or we can say hard questions, then, as I have suggested, that always first come up with a recursive or recurrence relation. Just imagine the bigger problem and just try splitting that. Okay, this is the bigger problem, and if I know the result anyhow of this problem, of a smaller problem, then how can I use that smaller problem to calculate the result of my original problem? If you can just come up with that relation, then you can solve any problem, right? Anyone have any other questions? And one more thing for tough questions, always try to represent function calls or function representations using in your notebook or something, so that you can visualize those things clearly, how the recursion is going on here, where it is stopping and where it is not, right? Okay, so I have also mentioned few resources to practice here. You can simply visit those links, and or you can also try those common platforms like LeetCode or Codestudio, and try the top problems that are asked in interviews, right? For practice, and when you practice around 15 to 20 recursive problems with 5 or 6 hard problems, you can confidently say that okay, I have enough command on recursion and I can solve any recursion problems. By any, that maybe not be 100% true, because each time there might be very unique concept that will be used logically in any problem that you might miss. But you can say after solving 15 to 20 problems that you are very good in recursion. Okay, and you can connect with me on LinkedIn to, if you have any further doubts, or if you need any resources to of anything around DSA or CP, right? So yeah, that's for the today's session. I think.
Thank you so much, sir, for this knowledgeable session today. Your depth of understanding of recursion and your ability to present the topic in such an interesting way produced one of the most memorable sessions. We appreciate our efforts and plan to learn more. Thank you again for your time.
Thanks, Mansi. It's my pleasure to teach students. Thank you.
Thank you. So, guys, right now we will be having a quiz regarding today's session. Kindly attend the quiz. Winners will be getting exciting prizes. Link is in the description box. You can check it out. Also, the link is only available for 30 minutes, so be quick with your answers. Now, I want to end this session with a quote. A good event never ends in the world. They take only a pause and keep us awaiting for the next. So keep hoping for the best and keep shining. And thank you so much for being such a wonderful audience. Also, special thanks to our sponsors Geeks for Geeks and Coding Minutes and our speaker Mr. Rahul Lather. Without them, the session would not have been possible. See you all tomorrow at the same time with another insightful session. Till then, keep learning and don't forget to give the quiz. Thank you.
So you think you know data structures well, but often get stuck when it comes to problem solving. Well, now you are at the right place. Welcome to Data Structures and Algorithms Level Up course. Hi, my name is Prateek and I'm a software engineer at Google. I have created this course for anyone who wants to learn how to apply data structures for solving coding problems and algorithmic optimization. In the past 5 years, I have taught over thousands of developers through my online and in person bootcamps that helped many students and working professionals in their careers immensely. This course will help you to develop a strong problem solving mindset and write cleaner and highly optimized code. This course is a highly practical course, and we will discuss over 100 problems of varying difficulty levels along with a complete hands on implementation. You will learn various tips and tricks related to concepts like recursion, backtracking, sliding window, two pointer problems, dynamic programming, pattern matching, graph algorithms, and more. Not just that, you will also learn by solving problems involving various data structures such as stacks, queues, linked lists, heaps, hash tables, tries, and graphs. With over 200 plus high quality video lectures, concise and simplified explanations for complex topics, this course is your one stop destination to master problem solving. Unlike most other courses, this course is fully interactive. You also get coding exercises and multiple choice questions to test your skills. The code judge ensures that your logic is correct and you get a real time feedback on your code submission. Doesn't matter whether you have a computer science background or not. This course is for anyone who wants to ace problem solving and achieve big. So what are you waiting for? Sign up today and I'm looking forward to meet you in the course.